Well, today we're going to be looking at a new section 4.3, and we're connecting actually the first derivative and the second derivative. So, incentives is that you will be able to use the first derivative test for local extrema. So we've used the candidates test, now we're introducing a new type of test. Secondly, you'll be able to use derivatives to determine concavity. And the third objective is we can use derivatives to calculate the point of inflection of a graph. So first of all, let's begin with the first derivative test. And this actually is something we've kind of been doing already, but we're just formalizing it. So the first derivative of test makes sense. We're going to find the first derivative. Now, in class the other day, we talked about that we can use the first derivative to determine whether a graph is increasing or decreasing, right? Because if the first derivative is greater than 0, then we know that the function is increasing. But if the first derivative is negative, then we know that the function is decreasing. Okay, fantastic. Now, how do we use that to be able to determine extremas? Well, when the derivative is equal to 0 or when the derivative is undefined, we know that we have critical values. Now, those critical values are possible points for an extrema. And basically what we can think of is if the first derivative changes from a positive to negative. So let's say I have a first derivative sign chart here with a critical point. And if it changes from a positive to a negative, that is the sign of the first derivative chart, then we can say that the graph has a relative maxima because the graph is changing, the graph of what you may say? The graph of first derivative is changing signs from positive to negative. Now the other scenario is here we have a first derivative sign chart with a critical point. But what if we change the sign of the first derivative from negative to positive? Well, then that would be a relative minima because the sign of the first derivative graph changes signs from negative to positive. Well, let's do an example of this. So, well, actually, we're not going to do an example. We'll look at one. So here we have a graph with a lot of turns. And we notice we've got an endpoint here. Now, this is the absolute minimum because the value is the lowest in the entire graph. Notice from this minimum, our derivative is positive. So the function's increasing. Okay? As we're going along, now we have a derivative of 0. Now, we notice here the sign of the function does not change. The sign was positive, the value of the function was increasing, and then it continues to increase. So this is no extrema value, but it is a critical point. And we keep increasing, increasing, increasing. Now we have a derivative of 0, so we have another critical point. And at this time, the sign of the first derivative is changing from positive to negative. So then we have a maxima. Now again, the function's decreasing, or the sign of the derivative is negative. And again, we have a derivative of 0, and we change direction. So that is a minima. And we continue increasing, and now we have where a derivative is undefined. So this is also a critical value, and it is a maxima because the sign of the first derivative changes from positive to negative, or the function changes from increasing to decreasing. Now we have first derivative negative, and we've got the first derivative equal to 0. However, it's not an extrema because the first derivative does not change signs. And last of all, we end with a local minima because the derivative is negative, so on the right endpoint, we have a local minima. I hope that makes sense to you. Now let's just talk a little bit more about. And if we're at a left endpoint, okay, so we're at the far end to the left of a graph, and if our derivative is less than 0, that means it's negative. So let's say this is an endpoint on the left, and if the derivative is negative, okay, so it goes something like this, let's say. Well, you can see then if the derivative is less than 0 at a left endpoint, then it is going to be a local maximum. However, if we're at the left endpoint, but our derivative is positive. In other words, the function's increasing, and then it continues of some fashion. Now this will always be a local minima because it's increasing from the left. Now, right endpoint has similar type patterns. Now here we're going to be at the right of the function, and let's say the first derivative is less than 0. So that means we're coming to the end of the graph, and we hit our endpoint. So you can see the first derivative is less than 0, it's negative, and so therefore now we have a local minimum. But what if it were to change derivatives at the right endpoint, like, for example, here. So now we can see our first derivative is positive, but instead of having a minima at the endpoint, we now have a maximum at the endpoint. I generally don't memorize them, I just make sense. So here we go for the first derivative test. So the first derivative test, if you look at your map that I gave you, we're going to first find the first derivative, right? That makes sense because it's the first derivative test. So we end up with 3x squared minus 27. Now, in order to have a critical point, either the derivative equals 0 or it's undefined. Well, in this case, it's not a rational function, so it can just be equal to 0. So now let us solve for x. So we add 27, then we're going to divide by 3, okay, and then we take the square root of both sides. So we get 3 equals the absolute value of x. So we end up with plus or minus 3 as our possible critical points. Now, looking back at the original function, are these values within its domain? Well, it is a cubic function, so yes. So we are going to consider the values of a positive 3 and a negative 3. Now, if we were doing the closed interval test, or the candidates test, we would substitute these values back into the original equation and determine a max or min. Now, the new technique we're learning today is we're still going to use these points, but now what we're going to do is we're going to make a sign chart, a first derivative sign chart. And on our sign chart, we're going to place our critical points. And we're going to be determining to the left and the right what is the value, the sign value of the first derivative. Okay, so if I go back here to my first derivative and I substitute a value less than negative 3, let's say negative 2. Well, negative 2 squared is 9 times 3 is 20. Well, that didn't work because, wait, I didn't go to the left of negative 3, so let's say negative 4. There we go. Negative 4 squared is 16. 16 times 3 is 48. 48 minus 27 is a positive value. There we go. Now we need a value between negative 3 and 3. I like 0. So plug in 0, we get negative 27. And then if I plug in a number greater than 3, like 4, again, I'll get positive. So we can see then, if I were to make a rough sketch of the original function, it's increasing, decreasing, increasing. So you notice the first derivative changes sign from positive to negative at negative 3. So therefore, we have a max. And the first derivative changes sign from negative to positive at x equals 3. So therefore, we have a min. So now we've identified where the max and the min occur. Now, if they want the values, then we would plug negative 3 back into the original and get the value. Same with positive 3. Plug it back into the original to get the y value. And just to complete that thought, if I did that, I already did the math. Negative 3 gives an output of 57, and 3 gives a value of negative 51. Okay, great. Now, continuing along, let's talk about concavity. Now, the definition to concavity might be a little confusing to you, but you can also just visually kind of figure it out. So the definition for concavity is here, where the graph of a differentiable function, y equals f of x, is considered concave up in an open variable if y prime is increasing. So that means the first derivative is increasing, or it means the slope is increasing. Well, if we look here, it's already labeled as concave up, but what do you notice about the slope as x gets larger and larger and larger? Don't you notice that the slope is increasing? In other words, my function is getting steeper. So if the slope is increasing, then that means it's concave up by definition. Now, concave down is basically the opposite. If your first derivative is decreasing, in other words, if the slopes are decreasing in value. Okay, well, if we, remember we read a graph from left to right. So if I start here, so looking here then we can see that it is quite steep at this point. And then as I continue reading this graph, it's getting less steep, it's getting less steep, it's getting less steep, it's getting less steep, less steep. So you can see the slopes are decreasing. The value of the slope is decreasing. So therefore it's concave down. Now, visually, I kind of like to think of it kind of as a cup. And when I look at my cup here, if my cup, you can kind of see the curve, it is concave down. And then my cup here is concave up. Now, of course, that's not the technical definition, but visually, I can recognize concavity. Now let's talk a little bit more about this. So if the first derivative is increasing, then the second derivative must be what? That's right, positive. So everyone write in positive. Because if the first, just like a function, if a function's increasing, that means the velocity or the first derivative is positive. And likewise, if the first derivative is increasing, then the second derivative is positive. Now, if the first derivative is decreasing, then the second derivative must be negative, okay? Now, this goes along with what we've just been talking about. Now, something I like to do is just a visual. If the second derivative, notice there's two pluses, if the second derivative is positive, then it's going to be concave up. Now, if the second derivative is negative, it's going to be concave down. Because if the second derivative is negative, then my first derivative is decreasing, which is the definition of concavity. Now, if my second derivative is positive, then that means the first derivative is increasing, which is the definition of concavity. So second derivative positive, concave up. Second derivative negative, concave down. So now we've addressed this third portion of your thinking map. And so you can see concavity is based off of the second derivative. Second derivative. So second derivative positive, concave up. Second derivative negative, concave down. Always go to second derivative. So now if we look at example where we need to determine whether the function is concave up or concave down, whoa, that's an interesting spelling of concave, we have to find the second derivative. Well, let's first find the first derivative, which is negative 6x squared plus 12x. And now let's go ahead and find the second derivative, which would be negative 12x plus 12. Now, they didn't ask us for anything about the first derivative. They just want concavity. So now if I need to decide whether it's positive or negative, the sign. So again, I'm going to set it equal to 0, negative 12x plus 12, because this is where I can identify where this function changes signs, right? Because we want to know when is the second derivative positive or negative. Divide by negative 12, x equals 1. So this is my critical point for the second derivative. Now I'm going to make a sign chart, but again, always label those sign charts because you get confused. What am I doing here again? So 1 is the critical point where the second derivative is 0. So if I plug a point less than 1 into second derivative, let's say 0, I get a positive number. If I plug a number greater than 1, like 2, I get a negative number. So we can say the graph is concave up on the interval, and we'll say from negative infinity to 1, since, this is your justification, the second derivative of g of x is greater than 0. Okay? And then we would say the same thing for concave down. The graph is concave down on the interval from 1 to infinity, since g double prime x is less than 0. You cannot use just the sign chart as a justification. You actually have to write a sentence based off your sign chart. And the last topic is point of inflection. I know this is a long video, that's why I'm not putting in questions in it. So a point of inflection is where the graph of a function has a tangent line and where the concavity changes. So in other words, the point of inflection is the point where concavity changes. So I have a couple pictures here. So if we look at the first picture, notice it's concave down and then it changes to concave up. Whoops, I meant to change colors there. There we go. So approximately the point of inflection is right there, the point where the graph changes concavity. Now in this second graph, I have concave up. Oh, I have concave up the entire time. So therefore, there is no point of inflection because there is no point where the graph changes concavity. Ha-ha! Now here, I have concave up, and then it changes to concave down. So approximately at that point is my point of inflection. Now, of course, if we're given the function, we can analyze it, but this we're just given graphs. Concave up, whoa, and then I switch to concave down. And then I switch back to concave up, the entire way. So my points of inflection are right here, right here. So I have 2 points of inflection that time. Now what do you think about this graph? How many points of inflection do you think there are? Well, decide how many times does it change concavity. 1, 2, 3. So it looks like I start off concave up, concave down, concave up. So there'd be 2 points of inflection. Now we have completed the entire template for that resource page I gave you. It's kind of exciting, huh? So now we know the last portion, which is points of inflection. And points of inflection, if I make that bigger, we can see that if the second derivative is equal to 0 or second derivative undefined. Notice these are basically, we're looking at critical points for second derivative. Now these are possible points of inflection. Remember that people just always assume it's a definite point of inflection. It's not true. You have to check. Because in order to be a point of inflection, it has to change sign. So then, whoops, sorry, I thought I was on hand mode. So then if the second derivative does change signs, then you have a point of inflection. If the second derivative does not change signs, you do not have a point of inflection. Well, our last example here, and we're going to find a point of inflection. Now remember, points of inflection are dependent upon the second derivative. So let's find the first derivative. So the first derivative will be y prime, and it's an exponential function. So it's itself, e to the negative x squared, and then it's multiplied by the derivative of the exponent, which is negative 2x. So if I clean that up, I get negative 4x times e to the negative x squared. Okay?